Hello, my name is Christopher Robert Stum, and this is the second of a series of 3 videos dedicated to explaining a process known as completing a square. In this second video, I'm going to be explaining the process of completing a square by using the definition previously established in the first video of the complete square. And thus, in the third, I'll be explaining various applications of this process. So, recall from the first video that we defined a complete square as x plus b divided by 2a squared equal to x squared plus b over a, x plus b over 2a squared. And we interpreted this geometrically as follows. Overall, the process of completing a square entails attempting to change a second-degree polynomial, that is a quadratic in standard form, such that it's y equal ax squared plus bx plus c. So where a, b, and c are real numbers, that is they are constants and a does not equal 0, thus that would disqualify this as a quadratic equation. We want to change something of the standard variant of a quadratic to the form a times x minus h squared plus k, where h and k are constants. If you want to think of this conceptually in terms of the geometric analog to which it could, I guess, be synonymous, think of it as if all of these are analogous to the sum of areas of separate figures, then we're saying, given these figures, how can we arrange them in such a way to form a perfect square that is a square that satisfies these criteria that we've established? More often than not, we're going to have junk left over, that is the k here. We're going to have some figures that just can't fit into the perfect square formed, and so the constant k here will account for that. Before I discuss the various techniques by which we're actually going to complete the square, I first want to just kind of give an analog that is a geometric representation of what this entails. So here we have an a times x squared, which can be signified also as a times x, and so this could be analogous geometrically to a figure with dimensions ax and x. And suppose that maybe the a makes the x a little bit wider, such that the width is a little bit wider than the height. And so here, that means that this in turn would be a figure with area, and thus dimensions x. Notice that this is x, so these are the same height, and then some width b. And then this is plus. Since this is a c, if we observe that there's an understood 1 in front of it, that is the coefficient of 1, this is actually a figure with height 1 and width c, so there's that. And that's the geometric representation of this. And so this equation is saying, since y is equal to some square value, that the area here is equal, that is, it is analogous to the sum of the area of each of these figures as shown here. So let's talk about the various processes by which we can complete the square. The first entails working one side of the equation, and again the goal is to change this into this. Now to do that, it requires first that we make this substitution. But before we can make this substitution, that is a perfect square, so before we can form a perfect square, we need to change this variant of the equation, that is the standard form, into this form. And so this first method entails only working one side of the equation to do that. So the first thing we want to do is isolate the x. That is, we want to remove the lead coefficients, thus we have x squared. So we can do that by factoring out an a, such that now we have x squared. And notice that by factoring out the a necessitates that I put a b and an a in the denominator, such that when I redistribute the a, I get a cancellation of terms, and thus bx. So the same applies for c as well. Now what this means geometrically is that I've factored out the a, and so now I have a figure x squared, and so its dimensions now x by x, and so we can imagine if this made it somewhat wider than normal, that I've actually just decreased the width of that shape a little. And in turn, this being b over a, suppose that, again, it makes it a little thinner, and so now this is a width b over a, and it's a little thinner, but still a height of x, and so here we have c over a little bit thinner, and that's the geometric analog to what's happened here. Now, to complete the square, notice that this is very much the same. This is x squared plus b over ax, x squared plus b over ax. All we need now is b over 2a squared. But before I actually add it in, I'm going to explain why its inclusion is necessary. So again, if the idea is to form a perfect square, that is to arrange these given figures in such a way that we can form a perfect square, first we need to have insight into what's going on here. So I want to draw your attention to something interesting, that is the b over ax, and observe that this is actually y equal to a times x squared plus, suppose we multiply this by a 2 over 2, analogous to 1, that is 2 over 2, and so we have 2b over 2ax. That is, we just multiplied it by 1, but we put 2 over 2 b over ax. Why would I do that? Well, observe that 2b over 2a x, that's actually equal to b over 2a x plus b over 2a x. So, because when we recombine these, we get 2b over 2ax, cancellation of 2 is b over ax. Why would I draw your attention to that? Because that means in place of the b over ax, we can substitute plus b over 2a x plus b over 2a x. And then we have our plus c over a. And this being, these two just being expanded versions of that. What does that mean? Well, since this is b over 2a, observe that this is a width of b over a. So if we multiply that width by 1/2, multiplying straight across, we get b over 2a. This implies that half the width of b over a is b over 2a. And so now this says that we have the addition of 4 shapes, and the 2 of which now change such that they're half the width of this one. And so now we have plus still a height x, and then skinnier still, so probably maybe here, a width of b over 2a, and then that's plus b over 2a times x, and we still have our plus c over a and times 1. And so now this is the geometric analog as that. Now it's more efficient to denote it simply in this form, it's more compact, but note that I expanded that, but it's still the same thing. So I just wanted to draw your attention to that. Now, observe that if we arrange these in such a way, that is, if we try to form our perfect square, this is a x and x, and so this is our x, and so since it's the length x, this is our b over 2a, and so this in turn is the length x, so we can put it right beside this, because they're equal in length, because their heights are all the same, and this is b over 2a, and this is b over 2a, and notice that because of that, it necessitates that this is a distance b over 2a, as is this, which this is why we must add b over 2a squared, so we can complete the square. That's why it's called completing the square. And so to do this, what this entails is that we have to be clever, because again, we're only working one side of the equation. So in this case, we would observe that this is y equal to a times, so then what we do, x squared plus b over a x, we want to again replicate this such that we can substitute that. To do that, we add b over 2a squared, so plus b over 2a squared, and then we subtract it, so minus b over 2a squared. The reason we've added and subtracted it is such that these will cancel anyway, and we haven't really changed anything. But the advantage it affords us is because then we can obviously substitute this portion and observe that that is a perfect square. And so we've completed the square, and we have our plus c over a. And that's all times a. So here, we've observed that what this means is that we have these figures, and we've, again, put them together as follows. We have our x and x. We have our b over 2a. And then we have our perfect square b over 2a, b over 2a. And as such, we have completed the square. But now notice that in doing that, we've kind of got two things going on here. So these have all been used now to make this perfect square. And as I said before, we have some junk left over. The junk, namely in this case, being this figure, which is a positive, but it's c over a dimensions 1 and c over a. And also we have the opposite of b over 2a squared. So if we denote this as positive, then correspondingly we also have a negative b over 2a, b over 2a. That is to say, this is the opposite of that, so we can denote that by separate colors if need be. But geometrically, we've again invented a clever way to complete the square, and so this is the junk left over, which is algebraically signified here. Alright, so the advantage this affords us is now we can make this substitution. So this becomes a times x plus b over 2a squared. Now we have this left over, and if we define subtraction as addition of the opposite, then it behaves commutatively, so we can reorder the terms such that we have plus c over a minus b over 2a squared. Okay, and that's all times a. So, and I'm actually going to distinguish these parentheses outside by these, that way there's a clear distinction. Now, we can make a further simplification by observing that we can factor the back in the x, and factor back in the variable a, that is the lead coefficient. So let's do that. This is going to be y equal to, so distributing it here, we get a times x plus b over 2a squared. Now, distributing the a here, we have a cancellation of a such that we have plus c, and then notice that this is minus. Now, before we distribute the a, let's observe that we can, by the property of exponents, distribute the square in here such that we have b squared over squaring a 2 yields 4, and 4a, squaring the a gives a squared. When we distribute this a, we get a cancellation of one of the a's such that the result is b squared over 4a. So b squared over 4a. That is, alright, a simplification. Now, what I want to show you is that this is now in the form of a perfect square. And again, geometrically we're saying we've used this, we've made a perfect square, here's the junk that's left over, which is signified here. So changing this form doesn't change the fact that this is still the junk left over. I'm just going to erase it to reduce the amount of clutter. Alright, so what we have arrived at is this equation. Now, again, I promised you that I would tell you what these values are equal to. Well, if you recall from the first video, we defined h to be equal to the opposite of b over 2a. And lo and behold, we have plus b over 2a. And note furthermore that since this is plus b over 2a, if we bring this down, x plus b over 2a really means minus the opposite of b over 2a. Because two negatives, so that is the opposite of the opposite, denotes positive. So if we substitute h being equal to b over 2a, then indeed that is the opposite of b over 2a. We see that this is x minus h, and so now we can write this as y equal to a times x minus h squared. And notice that here I said we'd have junk left over. This is all just denoted as being equal to k. And so we have now changed the quadratic from the standard form to a times x minus h squared plus k. That's the first method, where k is said to equal c, that is c minus b squared over 4a. So there's that. Now, the second method entails working both sides of the equation, so let me show you that real quick. In the case of the second method, we're again given y equal to ax squared plus bx plus c. And we want to, again, do the same change. However, we're going to do it a little differently. We're going to work both sides of the equation this time. So let's let y equal some value. The simplest one, I'd say, is 0. And 0 is a good choice because it's the easiest number to work with. So let's let y equal 0. So now we're going to work both sides of the equation. And what we want to do, the reason we chose 0 is we want to evaluate what the perfect square variable equals. And we'll explain the comparison, that is how they the two methods compare and contrast and what they really entail later. But for now, so we want the same thing, so the goal is the same. We want to get this in the form of x squared plus b over ax plus b over 2a squared. So we want to isolate, that is the x, the lead term, and so to do that, instead of factoring out an a, now we just divide both sides of the equation by a, such that we observe 0 over any number is still 0. And so by properties of fractions, we observe this as a over a x squared. Cancellation of lead coefficients such that we have x squared, so there we have the x squared, plus b over a, x plus c over a. Now, before we add b over 2a squared, we then want to subtract c over a from both sides, such that we have the opposite of c over a equal to x squared plus b over a x. There we go. So we've added the opposite of c over a, cancellation on this side, there's that. Now, lastly, we want to complete the square by adding b over 2a squared to both sides of the equation, because what we do to one in turn we must do to the other. And so this becomes b over 2a squared is equal to x squared plus b over ax plus b over 2a squared. And now this is in the form of a perfect square such that we can make the substitution. And I'm just going to write this the other way around. So this is x plus b over 2a squared is equal to, and again, I'm just putting this over here b over 2a squared minus c over a. And in this particular instance, we see that unlike the last time, we have just the perfect square on one side